All right, guys, in this video, we're going to go through 4.5, which is an introduction to probability. Now, you've probably seen probability before, 6th grade, 7th grade, stuff like that. We're going to be briefly recovering those concepts just to make sure you have a solid basis. But then we're going to dive into some deeper levels of probability, compound probability, and things of that nature. But to get the ball rolling, I want you to pause the video, and I want you to see if you can come up with the probability of these following events happening if I roll one die, a fair six-sided die. See if you can come up with the probability of these occurring. Well, hopefully you've done that, and hopefully what you got was the following. For an even number, I hope you got 3/6. Now, you might have written it a little bit differently. Maybe you said 1/2 or 50% or 0.5. I'm okay with however you want to write these, whether as a decimal fraction or percentage. But either way, some way of saying, hey, I think about half the rolls, half the rolls are going to be even numbers. The other half will be odd. For 6, hopefully you came up with 1/6, which I believe is around 16% if you do percentages. Number larger than 2, that will be 4/6, or 2/3, commonly known as 66%. Not a 5, that would be all the numbers that are not 5, so 5/6. And then not a 4 or a 5 is going to be 4/6. Again, roughly around that 66% mark. Was that too difficult for you? But let me give you a little bit of insight into what your brain is doing. You see, when we look at these, what our brain automatically does to compute the likelihood is it says, okay, how many possible events are there? Or what are all the possibilities? In this case, there are 6. When we roll a die, a fair die, it has 6 sides. Hence, that's where our denominator comes from. The number of all the possible outcomes. What is the top number going to come from? Well, that's going to be the number of events occurring that we're interested in, or the number of different ways what we're interested in could happen. You could think of it as, or looking at the first example, we think about there are 6 total possible outcomes when we roll a die, which is where the denominator, but we're only interested in 3 of them, namely the even ones. Hence the fraction 3/6. Now let's take a second and let's look at a die roller. Now we could pick any event here. I'm going to go with the first one, the probability of rolling an even number that we just looked at. And what I want to do is I want to test this. We said the probability of this occurring would be 3/6, or 1/2. So let's indeed see, is the probability of this occurring 1/2? So let's go over to our die roller. Okay, we're 1 for 1. 2 for 2. 2 for 3. 2 for 4. 3 for 4, or 3 for 5. And we are 3 for 6. We hit it right on the nose, 3/6. Okay, let's try it again. 0 for 1. 0 for 2. 0 for 3. Goodness. 1 for 4. 2 for 5. And 3 for 6. Okay, one more time. 0 for 1. 1 for 2. 2 for 3. 3 for 4. 3 for 5, and 4 for 6. Okay, 4 out of the 6 rolls were even. So we ran that experiment briefly. We ran it 3 times, and the first 2 made sense, right? We got 3/6, 3/6, but then something puzzling on the 4th one. We got 4/6. Yet I assume you're not jumping out of your computer screens or falling over in your seats at this happening, okay? But this should be somewhat shocking. We just said the probability should be 3/6. And it was for 2 cases, but why is it 4 out of 6? How is that okay? We're going to talk about that. First things first, the first definition I want you writing down, and you're going to write all these down. The probability. What is probability in a broad sense? Well, probability is the likelihood that an event occurs. Simply put, it's the chance something's going to happen. I have a 3 in 6 chance of rolling an odd or even number. There's a 40% chance of rain today. He is batting, or the probability of him hitting the ball is 30% because he's batting 300 right now. You get the idea. Okay, probability is the likelihood that something happens. But within probability, we can break it down into 2 categories: experimental and theoretical. What is experimental? Well, it's what's actually going to happen. We can define experimental as the number of times an event occurs, right? Me rolling 4 even numbers on the die roller, or 3 in the previous 2 instances, divided by the number of times an experiment is done. How many times did I click on that die roller? Well, I did 18, but I did 3 sets of 6. In the last example, when I got 4 even numbers, I rolled the die 6 times, hence 4 out of 6. Experimental. It's when you physically test something. Physical data results. Baseball hitting averages are based on experimental probability. Okay, it's how many times you got a hit. Theoretical probability, on the other hand, is what we think will happen. This is us sitting there going, there is a 3 in 6 chance that I roll an even number. We thought about it. We said there are 3 favorable outcomes, me rolling an even number, out of a total number of 6 equally likely outcomes, right? A die has 6 sides. A fair die will have an even shot of rolling on any one of the 6 numbers. So we look at the number of favorable outcomes divided by the number of equally likely possible outcomes. And again, the words might be a little confusing, but this broadly should make sense. Experiment is what happens. I define what I want to happen, whether it's rolling an even number, getting a 6, getting a base hit, and then I simply look at how many times we ran the experiment and divide the 2. Theoretical, on the other hand, I'm identifying again in advance, what do I consider the event I want to happen? And then I look at what are all the possible different events that can happen and divide the 2. But we must be careful with theoretical probability. We must ensure that the number of possible events that we put in our denominator are equally likely. We cannot just simply sum the number of possible outcomes divided by the number of, and on top have the number of favorable outcomes without the fact that the bottom is equally likely. Think about it like this. Let's say I think about the chance of an earthquake happening. We could say there are 2 possible outcomes when it comes to earthquake occurrence. Either the earthquake occurs or the earthquake does not happen. Okay, 2 potential outcomes. If I say then, well, an earthquake occurring is the favorable event, you end up with the logic that there's a 50% chance at any given time that an earthquake occurs. Now, we all know that's not true. Why? Because our 2 events that make up our denominator are not equally likely. It's not the same probability that an earthquake occurs as one not occurring. Okay? Another example. Think about if I rolled 2 dice, both 6-sided, and once I rolled the 2 dice, I added the numbers up. Well, what would be all your potential outcomes? Well, you could get a 2, a 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Any number from 2 to 12, from snake eyes adding to be a 2 to double 6s adding to be a 12, and every number in between. So if my favorable outcome is 2 dice summing to be a 5, do I then say that the probability of that happening is 1 out of all the potential 11 sums? No. Why not? Because your chance of getting snake eyes is not the chance of, or is not the same chance as you rolling 2 dice and them summing to be a 5. There's only one way that we can add or roll 2 dice and get a 2. But there are multiple ways that we could roll 2 dice and get a 5. Your outcomes are not equally likely. So in every instance, you cannot just simply add up all the possible outcomes or look at the number of possible outcomes and on top divide, or on your numerator have your favorable. You can only simply look at the number of possible outcomes to be your denominator when they are equally likely. If they aren't equally likely, like with earthquakes or with summing 2 dice, we can still figure out those probabilities. We just have to use some alternate methods. Another important definition is sample space. This is the set of all the possible outcomes. Typically, if we add up or look at the number of events in our sample space, again, tying to the definition above for theoretical probability, the number of events in your sample space, if they're equally likely, will be your denominator for the theoretical probability. But again, those have to be equally likely. The sample space itself, though, is not the number of possible events, but the physical set of all the possible events, right? If I'm flipping a coin, my sample space will have 2 items, but the sample space itself is heads and tails. If I am rolling a die, the physical sample space has 6 items, but the sample space will be the numbers 1, 2, 3, 4, 5, and 6. So sample space is our fancy math way of saying it is all the possible outcomes. Another definition, probabilities are always between 0 and 1. Now, do I care if you write them as a fraction, decimal, or percent? I don't. I really don't. But you do have to remember they're always between 0 and 1. And this makes sense when you think about percentages. 1 is the equivalent of 100%. 0 is the equivalent of 0%. There cannot be over an 100% chance of something occurring. Sure, your coach could speak in hyperbole and say, give 110% effort, but you're not going to sit there and say the chance that you go win your next game is over 100%. It's not possible, okay? 100% even in itself is almost impossible because 100% probability is certainty. You cannot lose the game. It would almost be better if the team walked in and forfeited. Now, how many times that's truly present? I'm not talking 99% chance of victory. I'm talking true 100% certain victory does not happen in the real world. Okay? Very rarely do we see things in life that have a 100% chance of occurring. Similarly, with 0%, this means maybe red is a better color. It means it never happens. It cannot occur. You will not beat that team, okay? Again, very rare in real life, okay? This is why on the Weather Channel, I don't know if the Weather Channel around you does this, but they should almost never use the phrases 0% and 100%, okay? That means you have to be absolutely positive that it will occur. Now, when you think about it in those terms, hopefully it makes even more sense why the probability can't be outside of 0 and 1. If 1 or 100% means 100% certainty, we can't be more than 100% certain, like it's going to happen. You can't be more sure than that. Consequently, you can't have a probability over 100%. The same is true for 0%. You can't have a less than a chance that it's never going to happen. If it's not happening, it's not happening. You can't get below that, so to speak, probability-wise. So again, your probability will be within the confines of 0 and 1. And I would really caution you, even though you can use 0 and 1, most real-world events will not be represented as a true 0% probability or 100% probability. Okay? Let's do a little bit of practice. Think about some theoretical probabilities. Again, take a chance, pause the video, see if you can figure these out. So what is theoretical probability? Again, this is the probability we think about, not when we physically execute. So what we're going to do is, if the events are equally likely of occurring, we can go ahead and just look at all the possible outcomes, and that'll be our denominator, and then the ones we're interested in will be our numerator. When I think about flipping a coin, is it equally likely that I get heads or tails? Absolutely. So there are two potential outcomes. However, I'm only interested in getting a heads. There is one heads on a coin, so 1 out of 2. Picking a 9 out of deck of cards, again, assuming there isn't false weighting in the cards, it's equally likely that I could select any card. And so we would say these are equally likely. How many cards are in the deck? 52. And within that deck, there are 4 nines. Hence, my probability would be 4 out of 52. Guessing right on a multiple choice problem, again, assuming the person creating the multiple choice test had no bias toward A, B, C, or D, what we can say here is, well, there's 4 options. And the probability of guessing right being you select 1, since it's multiple choice, not choose all, we would say 1 out of 4, or 25%. Again, I think you're going to find most probability common sense. You just have to be careful. Make sure your probabilities are in the confines of 0 to 1, and also ensure that if you are going to simply look at the number of values in the sample set to be your denominator, we're going to make sure those are equally likely. Otherwise, we have to go about our probability a different way. So the question comes, do the theoretical and experimental probabilities always match? Answer, well, we saw this earlier, no. According to our die theoretical probability, there's a 3 in 6 chance of getting an even number. We saw, well, that was true for 2 of our experiments. Our third had a 4 in 6 chance. So no, they don't always match. And how do we reconcile that? Why were you not shocked by that? Well, let me answer my question kind of with a question posed at you. It's probably somewhat rhetorical. Would you be more surprised if I flipped a coin 5 times and I got 5 heads, or if I flipped a coin 25 times and got 25 tails? Now, when you think about that question, the answer in your brain probably is the 25. Why? Because it seems more probable that I would flip the coin 25 times and get 25 heads, operating under the fact that heads and tails each have a 50% chance of occurring. This illustrates the law of large numbers. What is the law of large numbers? The greater the amount of data used in accounting or in calculating experimental probability, the closer that experimental probability will be to the theoretical probability. What does this mean? This means the more times I flip the coin, the more I keep flipping it, the closer I'm going to get to that 50% theoretical probability for heads or tails. Okay? If I flip a coin 5 times, maybe I get 5 heads. But if I flip it 30 times, well, it still might be unbalanced, but maybe it's closer. I'm at 20 heads and 10 tails. Even that would be a bit extreme. Then I flip it 100 times, 58 heads and 42 tails. 100,000 times. Maybe then I'm at 501,000 heads and 499,000 tails. Either way, you can see as the numbers get bigger, even if there may be a drastic gap, you go, oh my gosh, there's a 2,000 gap between 500 to 1,000 and 409,000. But if you look at the percentages, the more trials you run when you flip that coin, the closer the probability of getting a heads and a tails experimentally is going to get to that theoretical probability of 50%. This is, for a real world example, this is how casinos make money. Every casino game out there has an under 50% chance success. So even if you have a lucky day, lucky in air quotes, and you go to a casino and you win $10,000, how does the casino not lose money? Well, all of its games have a theoretical probability of under 50%. So the casino is just trying to get more and more and more people in the door. Why? Law of large numbers. Okay? The more people that play their games, they know that the closer they're going to get to that theoretical probability. So the closer they get to that theoretical probability, if the chance of the person winning is under 50% for each game, which it is, then they are going to get closer to making money, right? We assume 50-50 would be break even. So if that theoretical probability is, say, 20%, the casino's not worried if you get off with 10 grand of their money. What they're worried about is getting as many people in the door as possible. Because once they do, they know that the probability of people winning and the amount of money going to them versus the casino goer winning is going to get closer and closer to 20%. Okay? This is why casinos make money. And we see this all over the real world. Okay? Now, again, this is based on the trials being independent. What do I mean by that? Well, what I mean is when I flip that coin or one person goes and plays the casino game, it doesn't affect the next time the game is played. Okay? Or me flipping the coin, right? One flip does not make the next flip somehow more likely. If that wasn't the case, if the trials were not independent, then what's going to happen is that will kind of change things up a bit. But broadly speaking, for the law of large numbers, whatever the theoretical probability of an event is, the more it happens, or the more times the experiment is run, the closer you're going to get to that theoretical probability. Question to think about. If there's a 40% chance of rain, what is the probability it does not rain? As you think about it, let me switch my files over. And what you probably have in your brain is 60%. Okay? 60%. This, what you just calculated, is known as the complement. Not you look nice today, but the probability complement. It's the chance that something does not happen. And it's very simple to find. The complement of an event you find by subtracting the chance of the event occurring from 1. Think about it like this. If I, and you actually did this earlier, if I have a 1 in 6 chance of rolling a 4 with a die, what's the chance of not rolling a 4? Well, you immediately say, well, it's 5 out of 6. What did your brain do? Well, your brain said there's an 100% chance, if we look at between not rolling a 4 and rolling a 4, that combines all the potential probabilities. So what you're going to say is, well, I'm going to take 1 and I'm going to take away the chance of you rolling a 4, and now I have the chance of you not rolling a 4. It's pretty simple. The complement you just find by subtracting the probability that the thing does happen from 1. Okay? So if there's a 30% chance of rain, means there's a 70% chance it doesn't. The complement. Okay, we've gone through a ton of examples, or not a ton of examples. We've gone through a ton of definitions. Let's dive into examples and see how this is executed. Mr. Carter's Apple store was quality control inspected by Apple headquarters. Out of the 1,000 iPhones in his store, 4 were defective. What is the experimental probability of an iPhone in Mr. Carter's store being defective? Okay, we're looking for, when we read this problem, we're looking for the experimental probability. And by the way, take a second, pause the video, see if you can figure this out on your own before I continue. We're looking for the experimental probability, and we have in the back of our brains experimental probability. Hey, that's what's physically happening. That's what we're testing. So what we need to look for is how many times was the experiment run, okay? Well, they inspected the 1,000 iPhones. So that will be our denominator. What is considered a favorable event? Well, that would be, probably not favorable for me as a store owner, but the event we're focusing on or interested in, that would be an iPhone being defective. So how many were defective? 4. So what is the probability that an iPhone in my store is defective? It would be 4 out of 1,000. 4 out of 1,000, which we can divide. Let me grab my calculator. Which is 0.004 or 4%. There's a 4% chance that a iPhone in my store, or not, I'm sorry, 0.4%. There's a 0.4% chance that an iPhone in my store is defective. Continuing with the theme, you keep quality control specting, there's a 95% chance that MacBooks are working normally. And I have 452 in my store. Question becomes, how many are defective? Now this one's a little bit trickier, so let's think this one through. If we broadly look at probability, what we do is we take the number we're interested in divided by the total amount experimented on, and that gives us our probability. At least when we think about experimental probability. Now, when we're looking here, given the data, they actually give us the probability, which is a little bit different than last time. They give us the 95%. They also give us the 452. Now we have to really think about what this means because they don't give us the top number, but we got to understand what the top number means. What does X stand for? Well, there's a 95% chance the MacBooks are working normally. So if there's a 95% chance the MacBooks are working normally, then what I would do is take the amount that are working normally divided by the total that are in the store. So X is the amount that are working normally. Now, we are asked to find how many are defective. But again, before we can do that, we need to figure out how many are working normally. Well, here we you could think about it as a proportion, maybe putting the 0.95 over 1, or you could think about it as a chapter 2 equation. Bottom line, we need to get the variable by itself. Being divided by 452, so I multiply both sides by 452, and I find out that 0.95 of 452 equals 429.4, but I can't have 0.4 of a MacBook, so I'll just leave it at 429. And again, that's the number that are working normally. And this should make sense, right? Maybe you solved this a different way on your own. And you said, oh, if 95% are working normally, I'll just take 0.95 of 452. It's another way of thinking about it. We're doing the same thing. I just did mine in a little bit more of a formal math way. But again, this is where word problems, it's really important to understand, what am I asking you? You are being asked to find how many are defective, and we figured out how many worked normally. Well, what is how many are defective? It's the complement to the amount that are working normally. What do I mean by that? Well, I have 452 and 429 are working normally. If I subtract that, I should find the complement, aka how many are defective. So I run that calculation, and I find that roughly, again, because we rounded, 23 MacBooks are defective, okay? If 95% of the 452 are working normally, it means 429 are working normally, which means there are 23 that are defective. Guys, I hope this makes sense. As always, let me know what questions or concerns you have.